How's it going, everyone? Small here. So just a quick intro. Basically, I've spent the last decade building, breaking and fixing production systems. I'm also founder and principal engineer at Opulion, and basically we work the whole stack from the metal down from the model down to the metal. And I'm also like CTO of a tech defense company. So when I say this stuff has to work, I mean it. Okay, so in this video I'm gonna talk about specific situation where the agent won't stop working, and yeah, if this like basically this video is a little bit different from the other ones because it will be more technical here, and it's toward CTOs, technical teams, and more of technical founders than just like decision makers. So if that's you, just stay tuned. If not, you may read the article, which will be a little bit tailored to more non-technical founders. So here's the thing here. So the reason that the agent would not stop working, although like your team may already try to fix it, they may cap the loop, they may set max durations, and they just like all the day, but that not work. So the reason of all of that is not what anybody thinks. So let me just show you in this video the reason behind that and how you can fix it. Okay. So this is like a real system here. I just like changed the numbers a little bit, or at least enough that you can tell who the system is, and not enough that it stops being true here. So status is running, green dot, and every monitor on this thing says it's fine. And like this is actually the spend so far, and that's like 264 hours and just like 11 days. And notice that what it's not on this specific screen is like for this specific case there were no errors, no stack traces, no alerts, so everything looked great, but there's still the agent did not stop working for 11 days consecutively, which is like insane. Same bill. Okay, let's move to the next slide. So for this specific case, let's break it down week by week. So for week one, it was like $127, and that was that negligible that nobody would even like pay attention to that amount. And that's below like the line where yeah, like no one would check the invoice for just like $130. But for week two, it was like $1,340. Week 3, 6 grand. Week 4, 18 grand. And by like last like 264 hours already reached like 47 grand, which is like insane bill. So I want you here to look at the line at the bottom. So the one that you can barely see, basically sitting on the axis here, and that's what one bounded run of this exact agent costs, just like one run. And here's like what I want you to actually hold on to the next few, it's not few minutes, maybe it's like 45 minutes, 50 minutes, something like the length of this video. And basically like every single call in that system was bounded, like everyone. And the team was already smart, they already had like cap on everything, and on the surface nobody forgot anything, but still they got like insane bill. So we're coming back to this. Okay, so now before taking almost another 1 hour of your life, let's figure out if this actually if this like even a problem that you already have or not. And I'm not gonna do it with just like some random list of symptoms, because nobody would describe their problems the way symptom list does. So what I'm gonna do is I'm gonna describe it with a picture here. So first one is like plan and execute. So if you had like system where like planner makes plan and then hands it to an executor, then executor works on it, and then that executor would report back, then the planner would do plans of the report. or if you like have like system where the system is like generate and critic. What that means is like you have generator that writes a draft, and then a critic gives a note, then the generator would rewrite. So it's basically like the same shape here. Or if you have like this type of system which is called orchestrator and sub agent, where you basically hands out a subtask, sub agent does it, then returns a result. This is almost like the same shape again. And I want you here to look at like all these three different systems on the surface, and what do they actually have in common here. So basically they have two rules. Each one like these rules are like each one would cause the other, and each one on its own has specific limits. So one of these three is on like whiteboard at your company now, and I bet money on that. So basically, if you recognize any one of these type of systems, maybe it's a little bit more complicated because like maybe it's a more mature technology. But if we render it back to the core fundamentals, it would have this specific shape. Then this video is specifically for you, and I'm gonna show you how you can identify the issue and how you can fix it. Okay, now that I said who this video is for, now let's talk about who this video is not for. So basically, if this is your case, then you should leave because you should not care about this video. It's not for you. So if you're doing single shot completions, so basically if your system had like prompt in, then the model would run, then the response would goes out. If that's the system, and look at this specific type of system. Basically here there is no loop, nothing here that can run forever, cause nothing here even like would run twice in the first place. So this video does not apply to you, and you can just like go enjoy your rest of your afternoon. Or if this is like your case as well, for example, if your AI agent would write code against test suite, and look here at this specific diagram. So basically if you run the test suite, yeah, then you can get like a number back. So basically, for example, you're gonna get 41 failing, and that number would just goes like to the guard. So that's not the case for you as well. And basically, like if you count your failing test and then like put that number in the continue condition, that will stop when it stops going down. So it's simple as that. That's like the whole fix of this system. If you had the issue of an agent that keeps running, it does not require watching the rest of the video here. You can just like go build it and implement it right away now, and you just like can close the video. Okay, so look, like I'd rather lose the view here than waste your afternoon. And yeah, so here's what actually means for everybody would still be watching now. So if you're still watching, then you've got the hard case here, and the hard case is actually unsolved yet. So that's not me setting up a pitch here. That's like a real statement about where the current field is actually at, and I'll provide it in the next like in the rest of this video. And that's why this is like a long video, not like simple tweet or just like 5-minute video, because that would not give enough depth for you to understand the actual problem here and how you can not solve it, because it's not solvable, but at least you can prevent it 99.9% of the time, if you got what I mean. Okay, so let's start by doing a quick map here, so you know what you're in for here. So this one does not have any framework tutorial, no prompt tips. So basically we're gonna read source and draw and like share diagrams here. So first we're gonna read the actual continue condition out of like 9 different agent frameworks, and we're not talking about the docs here, we're talking about the source code itself. And then we're gonna like just like the theorem and why the fix your team already shipped nails that theorem completely, but still does not work on the real field. and then like 5 ways loop is gonna break, and I'll give you exactly a timing diagram for each one of these cases. And then the one that you're monitoring literally cannot see, what's like your monitoring cannot see and will never see, because that's like a sequence diagram, and it's the one that explain that huge build that we saw earlier. And then where like the 47 grand that we saw came from actually, and then like why nobody fixed this yet, and the seven like different fields that already solved this exact same problem, and what they've got that your current system does not have. And this is actually the part that decides whether you're gonna wait or you're gonna build this actual fix here. And last, what you should build, and also like what you actually, so basically like what you're gonna walk out from this long form video is you're gonna walk out with a decision about whether you should ship the thing that your team is building right now, or you should just like drop it, plus 5 questions that will tell you in just like 10 minutes if they've got it right or still not work in actual production system. And here I want you to notice, because you don't need to read the trace code here, that's like your engineer's job, and your job as CTO, as like technical founder, is to know exactly which questions expose the thing that they actually missed here. Okay, so let's start. Okay, so let's go look at this specific case. So for this one is actually like a line graph here. Here, so basically you're gonna have like a canonical agent, and from their own trace, I'm not paraphrasing here. Okay, so here as you can see should continue, takes the state, pulls the last message of the list, and then if that last message has 2 calls in it, it's gonna run the tools, otherwise it will gonna end. And that's the whole stopping mechanism here, that's it. That's like the entire thing that was gonna decide whether your agent would keep spending money or not, which is so immature for like such a framework. Maybe you don't understand this clearly, so let me try to explain it in plain English here. So basically the model would ask for a tool, and it keeps going and basically if it did not, then we're done. Okay, now I want you to read line 5 again here. So okay, so basically the loop stops when the model stops asking to continue. And I want you to sit with this for a second here, because that sentence is doing a lot of heavy lifting here. So basically, in other words, like the thing that decides if the agent is done or not is the agent itself. It's just like asking itself, and also answering that question by itself. And whether it's gonna say yes or no is that's the answer of this whole issue in this specific framework. And before anybody says that's only for line graph, it's only like a line graph issue, I hate to break it for you, but it's not just like line graph. Also line chain. Basically here the model would write the literal word, and it means like a final answer, and then you get an agent finish, and that's like string match on the model output itself. Also QAI, same like string match on final answer. Also even like OpenAI's own agents like SDK, so there are like no 2 calls on the response, and you're done. Also small I agent, you're gonna have like 4 code. Basically here these are like for this specific small agents, the model would call as final answer, and that's the exit here as well. It's almost like the same pattern again and again and again. And for all of these, basically 4 teams, 4 different code bases, 4 different frameworks, 4 different companies, no shared lineage, but all all of these like same like share like the same underlying issue here. And also like every single one who stops when the models basically like everyone who stops only when the model stops asking to continue, which does not make any sense. And then like everyone who chips like a second thing, for example, they may have like a recursion limit which they're gonna put to 25, maybe like max iterations which they're gonna put to 15, or they're gonna use variable called max iter for like crew AI, it's gonna be set like for 25, etc. As you can see here. So basically, like that's how the AI agents framework are actually like built. So basically, our built the architecture is built like based on the model's opinion itself, and plus counter, and that's like both the halves of this entire system they have. And to be clear here, that's not just like one framework being sloppy, as you can see. That's like every like agent frameworks in production these days. So all of them would have like the same 2 ingredients, which is like stupid if you're gonna ask me. So now let me draw like the loop for real here, and I want you to forget the code base for a second. Let's see the actual technical diagram of what's going on. So as you can see here, we're gonna have like a control flow graph. So basically, we're gonna start up at top. The model is gonna run. Then like we're gonna find that diamond. That's like your safeguard. If the safeguard says yes, you go run the tool, and if he says no, then it will not run the tool. And that arrow is basically is gonna loop you back around if like unless like the guard will tells no, so it's out. That's the whole system. And if you're gonna look at this specific case, like just like one loop back, one guard, that's the whole agent frameworks like architecture. If we're gonna render it to the first principles and to the basic stuff, that's how all of them are currently working. So here's what that means for your team, for your specific solutions, etc. So every question about whether this thing would stop or not, it all comes down to one diamond. Nothing else like in the picture can stop this. And so let's crack this specific guard open and see what's actually inside it and how it's going to manage our whole system to determine if we're going to stop or not. So first thing in here is like we need to understand like, did the model ask for a tool? And that's basically the model opinion. Second thing is like n less than max iteration, so that's the counter. And third thing is like there's nothing, like anything about the guard. That's like the complete list of everything your loop gets to look at when it decides like whether to keep going on, or it's just gonna or like it's gonna keep working, it's gonna keep charging you or not. Only on these 2 variables, which honestly is super stupid. Okay, so now let's get back a little bit back, like let's check history and like different types of systems so we can drive actual solutions of what people spent decades building, and then we can apply it to the AI. Also, this will help us understand better the problem, because although like AI agents are new, although machine learning is quietly new field, the patterns like the technical patterns would still appear in different scenarios. So for this one is about 1967, and this quote is from Floyd itself. So basically the quote says, proofs of the termination are dealt with by showing that each step of program decreases some entity which cannot decreases indefinitely. So this may sound old English. What does that mean in plain English? So basically, if you want to prove a loop stop or not, you need to find a number, and that number's gotta go down every time you go around the back edge, and also it cannot go down forever. So basically, it has to hit floor. That's the thing in plain English. And that number's got a name actually. It's called variant. It's like a function of the actual state, and it goes down on the back edge, and it's gonna map like into something with actual floor. And well-founded just like means it's get a bottom, and it cannot go below that specific bottom. So that's like the picture, just like step down, step down, step down, and then you hit the floor, and you cannot pass it. So just look, you gotta stop here. You cannot move past this. And yeah, this is like simple visualization here, as you can see. So here's like the hell that everybody skips when they build their AI agent frameworks, and most teams just implement these frameworks blindly. So basically, it's like an if and only if situation. So for these, like there's no like here's one good way to prove it, or like if a loop stops, a variant exists. Basically, like if a loop stops, variant exists, and there's like it's there whether you're gonna find that variant or not. Also, there's no second technique, there is no third option. This is like the only tool, and it's been the only tool for over 60 years now, so it's not new. Okay, so now let's point at the guard. So for the guard's case, what actually got decreased? Okay, so here's the guard. Let's check it out again. Your team maybe already answered this one. It's actually max iter minus n. And yeah, let's zoom a little bit more here. So look at the specific graph, because this is exactly what. So basically, it's gonna go around the back edge, and it goes up by 1. So like max iter minus n goes down by 1. That's a natural number. So at the end, it's gonna bottom out to 0. And function of the state, because n is the state here, and it will just like goes down on the back edge. It's gonna have like floor, which is 0. That's a variant, and that satisfies Floyd completely. And that's like a real Floyd variant here, not a hack, not a band-aid. That's a genuine termination proof, and that loop probably stops. So if you ever hear somebody say AI agent frameworks have no termination proof, they just like didn't read the actual source code, and you can shut that person down in just like one line if you've actually read Floyd. And I'm not gonna be the person here. So basically, like, your team shipped real proof, and the thing ran for 264 hours. So this is the big one. Like, what's going on? So why it's still running? And yeah, so let me try to explain the reason behind this. So instead of just giving you some like statement and tell you just believe me, I'm gonna actually give you a tool, thinking like mechanism, so you can so you can understand how this actually works and how you can actually fix it. And this would help you not just like in this case, but in many other cases as well. So use this like on any variable in any system, like this forever. This like it's a universal technical tool technique, if you want to call it that. And this thing would only take about 10 seconds of your time. It does not take that much. So basically, if you're gonna delete it and you're gonna run the same thing again, you're gonna see what actually changes. And basically that's the test in a nutshell. So basically what you're gonna do is like you're gonna delete a variable, and the system was gonna behave the same. If the system behaved the same, then the variable was never doing anything at the first place. That's like thing in if we're gonna render it to first principles. So now let's talk about the case of TCP. So let's say, for example, if we're gonna delete cwnd. So the basically here it's, if you don't know, it's the congestion window. And what's gonna happen here is like the throat pot would gonna fall off a cliff, and that's not like a hypothetical scenario. That's actually congestion collapse, and it actually happened before many times. And also like if we're gonna go back in history, and we're gonna talk about 1986 situation. So basically that caused the internet to fell over like Berkeley to the lab, and basically like 400 yards apart, just like dropped from 32 kilobytes to 40 bits a second, like 1,000 times worse, just because of this specific mistake. So what that means is like what that proves is actually like cwnd's load bearing. So if you're gonna delete it, the system would just like stop working. That means like that variable is actually doing real work in the system. Like it contributes a lot to the system. Now let's compare that to your agent's case. So let's say we're gonna delete the max ether. Let's delete this variable, and what's gonna happen is like it's gonna do exactly what it was doing before. So it's gonna do the same tool calls, the same order, same everything, and the trace basically doesn't even flange at all. What that means, like the same behavior and just for a little bit longer. And that's like the whole like thing right here. That's like the whole reason behind all this issue in a nutshell. So basically, like one of those two variables, like the one that we saw here is cwnd. It was like load bearing variable, and the max iteration for your agent case was like just like scaffolding, just like a variable that you can delete without changing behavior, or basically not changing anything in the system. Basically, it's useless, if you want to call it that. So if that's not sharp yet, I want you to watch this specific thing. So here we have like an infinite loop. This loop does not stop, and everyone would barely like coding knowledge would understand this. It's not like something extraordinary here. But now let's say if we're gonna add a counter here, let's say like that counter would count down from 1,000, and then it's gonna stop. So provably the same argument as yours, the same quality as the same quality of proof. I just like could publish this, and the loop does exactly what it did before, just like it does it 1,000 times, and then it's gonna stop. And that's here like that's like the counters just got specific name in formal methods. What the name of this thing is called actually ghost state. So what that means is like state that you're gonna add to make proof go through, and that means that like nothing on computational level gonna change. So basically like you can erase this thing without changing the behavior of the system. So my proof here is actually real, and my proof is worthless. Both are actually true here. So basically like a method that proves everything, proves nothing at the same time. And by this time you may be like a little bit confused. So let me give you a different example here. So this one is actually I want you to walk away from this video with. And this is how I would put it to a board if you have like a current like technical board, or like a board in your current startup or company, or maybe you're talking to investors about the specific situation. So basically if we're gonna talk about max iter variable, it's different from each of the agent frameworks, but you got the point here. So basically this variable is actually fuel gauge, And the fuel gauge is actually real, it's accurate, it's not lying to you, and it generally helps you like how much like to determine how much fuel is left. And when it hits the E level, like the fuel is out, the car will stop. That's actually guaranteed, and the gauge would work. So technically, like, or at least logically, the car would actually stop on the side of the road when you hit the E. And there are two reasons it could have stopped here. It's either like you arrived or you ran out of gas. These are only two logical options here. And both of these is actually like end the trip, and the gauge can't tell you which one's which. Uh, Also, it's not broken here. It's just like working perfectly, because the whole goal of the gauge is measuring fuel, and your question about whether you arrive to your destination or not have nothing to do with the fuel question in the first place. So basically, both of these are different questions, and basically that's max iter, and that's like the whole usage of max iter. It's like the gas gauge, it's like the fuel gauge, and just like you've been reading that like it's actually like a progress bar, where actually it's not. Okay, so now let's move to the code. So also, like, your code cannot determine that as well. So for this example, this is from LangChain code base, and this is what actually comes from actually. So as you can see here, top one, real answer. So basically the Q3 figure is 41.2 million. Bottom one bottom one kept tripped. The agent was stopped due to iteration limit. Now the same class, same field, same type, and so basically, like, what does your caller do here? Basically, it's just like string comparison on the output text, or and this is actually what happens. Nothing at all. So, like, tripped cap becomes an answer, and just like would keeps going downstream, and something like would just like write it to a database, or maybe sends it to a customer, or just like feeds it to the next agent. So in other words, the failure isn't the loop actually being stopped. The loop when it stopped is actually was correct thing to do. The failure is that it stopped cause I gave up, and stopped because I'm done, are two different scenarios. Although on the surface level here they would look identical, and like every layer downstream would believe the second one. So that's the case. Okay, now let's go back to Floyd. So basically, Floyd gave us four requirements. Yeah, let's just break each one on purpose and see what falls out. And basically, like, this is a checklist, not partition here. Basically, like, 3 and 4 overlap constantly in actual real systems. So let's get started. First one is no measure at all. So for this one, like, nothing anywhere in the loop measures remaining work. Second thing is like the measure is not a function of state. So we're gonna have like same state, which is gonna ask twice. So basically we're gonna get two different answers. So that's what like ask the model if it's done type of answers. Well, what is gonna like get you. Now 3 is like there's no floor, so we're just like gonna keep subdividing to infinity it will never land. And 4 is like it won't go down, so basically we're gonna have like flat line. What that means, like, the iteration happened but nothing actually moved. And 5 is, yeah, 5 is like it's gonna go up instead of going down, so the work gets undone or maybe like forgotten. And that's like the whole space here, like those are the only ways like a loop was gonna fail to stop. And the reason I can say only is because like Floyd only asked for like 4 things. So basically like break one of four and you're gonna get like 5 failure modes, cause doesn't decrease, splits into flat and increase, and that's it. So I went like and read the source of different line of AI agent frameworks, and here we're gonna break them into 3 columns. And does the continue condition check model opinion or not? Does it check counter that's got nothing to do with your task? And does it actually check real measure of remaining work or not? That's what this slide is about. So let's start by talking about line graph, line chain, crew AI, opinion counter. So also there's like AutoGen, OpenAI, small lag agents, opinion counter. Also we're gonna have like Pydantic AI, Vercel, AutoGPT, saying like opinion and counter. And the third counter here, column here, is empty on purpose, no? So basically we're gonna have like 9 frameworks, different organizations, different design philosophies, different languages, different years of production, but all of them have the same empty column here. And I want to be careful here because it's not gotcha. It's not like, whoa, I'm like so smart that I found out something that all these organizations, all these smart teams did not found. I'm just like gonna go back in just like 15 minutes or so and show you exactly why like every one of them is like this. It's actually on purpose, and it's not cause like it's not because like they're bad at their job or they're not smart. It's not because they're smart. But the fact here is the fact. We need to be subjective here. We need to say reality as is, and basically like nobody is measuring this task. That's the whole truth. So you can check this here. Okay, but for this one, actually, one exemption that actually worth calling out by name, which, cause actually it's the one that I cannot defend at all, which is like AutoGen's group chat manager. So basically, they're gonna have like max consecutive auto reply, which is like the default, and that's like 9 quintillion. Like every defense of loop cap like defense bound. It's like safety net, stops runway, bounds the blast radius. Okay, that's fine, but none of that defends this number. Like that's not bound. That's like decoration shaped like bound. That's crazy. Okay, now like the one that nobody sees common at all, which is like sub agent with hangs. Okay, so we come back. So like the one thing that nobody sees common is sub agent hangs, and here, as you can see, is the timing diagram. There are 3 different signals and one shared time axis. And if you've ever put a scope on a board, you already know how to read this thing. So let's start by top one. So top trace is the tool call. It's toggling. Let's say, for example, there's like an issue, return, issue, return. That's super healthy. Then it goes high and stays high. And that's like a call that went out and never come back. Basically, it's stuck here. The middle trace is that's your variant, max ether. And basically it's max ether minus n, so staircase down, 7, 6, 5, and then just like just flattens, and it's frozen at like 11, frozen at 7, sorry. And here at the bottom trace there's like the wall clock and still ramping, and basically doesn't care about what happened. So here's what actually happening. So the loop, oops. So basically, like the loop does zero more iterations, and if the loop does zero iterations, then the counter does zero decrements. So it's gonna hang for the infinity. And also another thing is like max iteration can't fire, and we're not talking about slowly can't fire, but never, like it's frozen at 7 for like infinity. And here's like the bit that should bug you by now, which is like Floyd's got precondition that he never wrote down, which is like from any non-terminal state, steps gotta be enabled. So basically, like decreases every iteration means is like basically it's like trivial, and it's true when there are no more iterations, but your proof is still perfectly valid, and your loops is just like hang here for the infinity. So both of these statements are true at the same time, and that's not a contradiction here. It's just like a hole in what the proof ever promised you in the first place. As you can see. Okay, so now let's talk about twin time, and let's go one layer down here. So as you can see, like you may be asking, like why does every watchdog in embedded like every single one what it does like count time instead of counting actual iterations here? And what I mean here is like everyone, like this is just like style thing, is something universal here. So because like this is like a variant that the loop drives, the loop with increments in like increments n. So what that means in plain words is like dead loop would never trips it. So in other words, like the thing that you're trying to catch is the thing that you're relying on to catch, relying on in order to catch that thing. It's like a dead end. Okay, and okay, so you can see. Like in that one, runs off an oscillator. So basically, we're gonna see like separate crystal, separate silicon, but the loop like would not be able to stop it. Just like it fires whether or not your code is alive. So yeah, what that actually means is like watchdog's variant is actual time here, because time is the only thing that will still be going down while the loop is dead, and that's why it's actually separate hardware here, and that's not paranoia at all. Basically, that's not it's not belt and suspenders here. It's the only design possible that would survive the exact failure. Like it's going to be there to catch in the first place. So here, just to summarize, like same failure, just like one layer down here. In other words, like your AI agent would be hanging, and a hang like firmware loop are the same bug, like between hanging agent and hanging firmware. And for the hanging firmware, they already solved it many years ago, like we're talking about in the 70s, with just like crystal and a counter. So that's to keep that in mind. Now let's move to the next thing. Here let's talk a little bit more about the embedded, and what's like actually make this even better, and this is actually one of my favorites. So windowed watchdog is actually like basically for this one you don't just like gotta kick it, you gotta kick it inside the window, T min and T max. This is like the window, the min and the max, time min, time minimum, time max. So if you're gonna kick it too late, you're just like gonna be hang that there, and everybody knows that one. But also if you're gonna kick it too early, then also that's also fault. And I want you to think about why here. So if you're kicking faster than the real world could possibly finish, what you're gonna end up doing is like you're not doing any real work at all. You just like keep spinning forever. So too slow means hang, too fast means spinning, and one instrument that would give you two different edges, which is critical. And here's the thing basically. So you already ship both halves here. Mixed iteration catches the left edge, and this pin as well. And walk lock timeout would catches the right edge, which is like the hang. And this I think is like that nobody ever told you before that they were opposite ends of like the same instrument here. So what you should do is like you should tune them separately, and that way like you need to set max iter for the spin, and if you're gonna do that you'll be surprised it does nothing for the hang. And neither of them would be looking at your task in the first place. Okay, so this is the one here. So basically if you're gonna take one slide out of the whole video, I want you to focus on this one specifically. So for this one there's like a sequence diagram. As you can see there's like planner on the left, executor on the right, times goes down the page, and also like I put like MU A in the left gutter and MUB on the right gutter, so that way you can watch both measures at the same time. Okay, so what's going to happen is like here planner would make plan, then he's going to have like 3 different steps. MUA goes 5 to 3, so basically it's descending, and it's actually doing its job perfectly. Now let's say for the executor would work the plan, so it's gonna like get the first done, then it's gonna block by the second one. So for this one like MUB 4 to 2, and which is also actually descending here, and it's actually doing its job perfectly. So what ends up happening here is like the planner would replan again, and that's totally normal behavior of what it should do, and because that's what it's designed to do in the first place. And here I want you to watch the right gutter, and basically I want you to see what's gonna happen to MUB. So as you can see, it's got reset to 4, MUB got reset to 4, and what that means like executor works the new plan again, 4 to 2, descending again, planner with replans, MUB with the resets again to 4, the planner resets MUB again, the report resets MUA, and in the end like neither of them would be doing anything wrong, and that's like how the planner is designed in the first place. That's like system architecture thing, and also like that's what the executor do. So both the planner and the executor are doing the right job, but the way that they're interacting together is wrong. So basically like MUA exists, which is like function of state, which is like also like well founded, and also like strictly basically like it's also like strictly decreases, and all 4 requirements exist like every single step of these. And the same for MUB, like it exists, it's a function of state, it's well founded, strictly decreases, all 4 exist, and every single step it works perfectly. But so the thing is like both proofs hold, like, and what ends up happening is like when putting these in the system, that will just like get hold like every step, and just like the system would hang and would never stop. And this one is actually not about it's not like about me being clever here. This is like a known result thing. So what I mean is like the union of 2 well-founded relations is not well-founded. It's not like because most people determine like if something is correct and something else is correct, if you're gonna put them together the result would be correct, but that's not the actual case. And this thing is actually a known theorem like released by Podolsky and Rybelchenko. Probably I butchered his name back in 2011. So this is like well-known theorem here, like in systems. Um, what this is about is actually two correct termination proofs. So if you're gonna compose them together and the composition has no proof at all, and there's nowhere you can stand inside either component and see it. So what ends up happening is like this result as I walked you through. And basically, like this whole video is trying to explain this point here. So I want you to take this like home with you. I want you to focus and understand why actually this is happening because of this type pattern. Okay. Now, here's the actual like same five exchanges, just plotted, so you can see them better. MUA and MUB, both the planner and the executor here. So the cyan one is the planner, the blue one is the executor, and that's like the shape here. Let me move my face a little bit down so you can see better. Okay. So now each one of these like would descend like every single time forever, and neither one would ever hit the floor because the other one would just like keep lifting it up, as you can see. And like a per component progress check passes on both of these, and every time you look, what you're gonna see is like both of these components are actually descending, both of them are healthy, both are fine, and this is like the failure that your monitoring is structurally incapable of seeing. And not your monitoring is bad here, we're talking about structurally incapable, and these are like this actually like no per component check that would be able to catch this, because the per component thing, and like in that level nothing is wrong, everything works perfectly. It's about how they interact together. And here maybe like you raise your hand, and maybe like even like you did that like an hour ago now almost. So basically like the same three diagrams, same topology, MUA and MUB on just like every single one of these. So this one isn't about an edge case here, and it's not framework bug that you can wait for somebody else to patch. It's actually your architecture diagram and this like why you're in this specific position here now. Now here is how that would look like on an actual dashboard. So as you can see, the planner would say that it's healthy, sub goals would still be remaining. Also it would look like it's descending, so that's like nice clean line. The executor as well would show that it's healthy, sub goal is still remaining, it's also descending, which is also like nice and clean. So on the surface, what you can see is like the system is running, and also like 264 hours like for like 47 grand like 47 grand like put on the system to run so far. And like both like those panels are actually correct on their own, as we saw earlier. So that's exactly what I wanted to get here, because both of these are actually correct and nobody is lying to you, your team is not lying to you, because both measures really are descending, and the alert would never fire because there's nothing wrong with either component on its own. And this is the dashboard your team is gonna show you when you ask if it's healthy or not, and as we saw before, does not reflect the actual reality here. So here's the actual decision that you need to make, and this one is actually yours, not your engineers, nobody else, not consultants. No one can make this decision but you. You should make this one, which is also a little bit hard decision to make here. So basically the decision is like, does your task have computable residual or not? And in other words, like in plain English, what that actually means is like, is there a number that you can calculate in code without asking a model that can actually get smaller as the task gets closer to done? Yes or no? If yes, then you can test, and it will be like an error bound, can have like proof obligation, count of closed sub goals, and you can just like put it in the safeguard. And basically the fix for this one, it will take you just about 3 days max, and you'll be all good to go. And you don't need to do any complex re-engineering of the system or stuff like that. Now, if the answer for this question is no, then I want you like to write like, for example, if it's something like write me good market analysis, then for this example there will be like no specific number there, no residual. Then the next question that you need to ask is like, can you manufacture a number or not? So for example, like here, rubric with score, which is like a verifier that's deterministic, and basically it's going to be generated multiple tests, and that's the actual work in this situation. That's the real engineering, how you're going to figure out or manufacture the exact number for this case. And this number would be traceable, and it's where I would put for me personally, that's where I'm gonna put my people to focus on if that's the case of the system. And the other case is like, if you try to manufacture it but the result is like you cannot, there's no way to manufacture a number, then you need to accept this harsh reality, which is like you should not ship any autonomous loop for that task. What that means is like, what you should do is like you need to ship bounded assistant with human terminal state, which means like in simple words, like this tool, this functionality needs a human in the loop. It will not be fully automated. That's impossible to do. And here I want you to notice what that says about the framework authors here, because the ones who shipped you a counter for that last branch, what they did is they did the honest thing here. They refused to take a measure that doesn't actually exist. And honestly, I'd rather like have a counter and know it's a counter than just like having a fake progress metric that I would believe in. Okay, now let's go back to the money side. Cause like I left you hanging almost like now 15 minutes ago. So Crew AI, basically it's gonna take like 25 iterations. That's the default one. So we're talking about 17.50 bucks. Lang chain is gonna take like 15 iterations. That's the default one. It's gonna cost you around 690 bucks. 6.9 about now. Let's say like against $100 for scale. So the cap here does exactly what it was promised. Basically it's gonna bound one run to rounding error, and that's the uncomfortable part here, because and I'm not gonna dodge this one, because this is like the harsh reality here. The cap works and does the job it was built for. So now the question is like, if you can cap this by $100, then where does that 47 grand come from in the first place? And that's like the $1 million question here. Okay, so this is the call tree here, and every node is an agent run, and every node is actually capped at 25 bucks, or sorry, 25 iterations. So let's check depth 1. So we're gonna have like 25 calls. Depth 2 we're gonna have 62.5. Depth 3 we're gonna have like 15,625. And next one we're gonna have like 390 over like 390,000 calls. Basically like every node on that tree is capped, and every node is individually provably bounded by like specific budget. And I can write you like termination proof for any code you would point at, and the thing is like nothing would balance the actual depth here. So what you should know is like bound on a loop is not bound on a system of loops, which is critical difference between two. So it's like there's a critical difference between the two. So basically, like every call was bounded, but the overall system was not bounded when it was put together. And that's like the sentence from slide 2. And that's what I asked you to hold into that. And it was true the whole time. And it's exactly why the bill, like that bill, like the 47 grand actually happened for that client. And just like one more thing here, because people when they ask, it's like never tripped rate limit here, not even once. Like over like the last 11 days of that system been running, uh, never did make any of that type of mistake. Never hit the rate limit, because like rate limits is a variant on requests per minute, and this thing was never fast enough. The issue was it was endless, and those are so different failures, and your rate limiter doesn't know about the second one, it only know about the first one. So here's the actual continue condition of that system. And why not verifier approves draft, then you can revise the draft. So basically we're gonna have like two agents, and an analyzer and a verifier. So what's gonna happen is like the analyzer would write, the verifier would rejects, analyzer would revise, verifier would rejects. That would keep happening for 11 days. So the loop would stop when language model is satisfied, and that's not a function of state here, because you can call it twice on the same draft, and what's gonna happen is it's gonna give you like two different answers. So that's failure mode number 2 here. This like straight off the checklist. And here like the part that gets me tripped here. So the component here, as you can see, it's named verifier, and it's actually exactly the component that every working system would makes it deterministic. So basically they call it a verifier, and in reality it verifies nothing. So it had an opinion, it was not bounded by any deterministic reality. So because of that, it ran 400,000 times, and now you paid for that instead of paying for only one run. So now the part that was gonna decide whether you're gonna wait or you can build or keep building what you are doing right now. So this problem is not new. It's as I told you before, it's not about AI here. It's not about machine learning. And outside the AI and machine learning space, it's actually been solved before, over and over again, in different fields. And these fields like have nothing to do with each other, and like mostly don't even would never like read each other's paper because they're so distinct. So let's start by first one. So yeah, first one is Walt. It happened like in 1945. So this one was like a sequential probability ratio test. So the situation is like computes log likelihood ratio. It's gonna compare it against two boundaries, and that was like the stopping rule. And it's back like from World War II. So they used it for munitions inspection, stuff like that, and to work back then. Now next one. Let's talk about clinical trials, which is like also mission critical domain. So for this one, it was about conditional power against futility threshold. And for this one, like this, how actual trial would get stopped early when it's not gonna work in the first place. And there are actual people alive because that rule exists. Next thing is Bayesian optimization. And this one is actually expected improvement, and it's against the cost of the next evaluation. Next thing is bandits. So this like confidence bounds against separation criteria. Move this down. Next one is about like Jitten's index. It happened like 1979. It's like an index against the other arms. And also like proof assistance. Basically here you're gonna supply the measure yourself, and it won't even compile until you do that. That way like you're gonna lean with if you but yeah, that's another case. So basically, like now let's compare to your actual agent loop here. So for your agent loop, it's gonna compute nothing, it computes nothing, and it's gonna compare it to constant. So now let's talk about like what does every one of these already proven systems have that your actual AI agent systems doesn't have. So first of all, like for Wald, let's say talk about the model of the task here. So Wald's got parametric model of the observation process. So for him, he knows what the data generating process would looks like. For clinical fertility, basically they got like a model of the trend and also the remaining curl. So basically it knows how many patients are actually left. Now for Bayesian optimization, basically it got Gaussian process over the objective, and that's an actual surrogate model of the thing is optimizing. Next thing is bandits. For this one, it has like reward distribution per arm. Fourth thing is Gittins. It has like an independent Markovian arms. And last thing is like and Lean has U. Basically, it refuses to move until you're gonna hand it over, like you're gonna hand the condition to stop. Now let's compare that to your agent. So for your agent's case, it got like model of language, and also it got no model of task in the first place. So here's like the general statement here, and this is the intellectual center of this whole video here. So basically, like every computed stopping rule, like every device needs a model of the task. Like every single one of these that we talked about, Wald, clinical fertility, all of these, Gittins, all of these had like this specific rule, model of the task. And like that's been happening across 80 years so far, and over 7 different fields that don't even talk to each other. And that means like, in other words, this is not coincidence here, and it's not like an implementation details. This is an actual pattern, this is a requirement, and this is how you can solve this type of issues. And for our case, like the AI agent case is for the LLM, it would get a model of language, and most likely it would not get a model of task. In other words, it's gonna miss the stopping rule, and that's gonna keep it like oversight. And this is like the direct consequence of the thing that gonna makes it general in the first place. So now let's be fair about let's now be fair to this specific field, because I promised I would not be biased here. So for Bayesian optimization, for them expected improvement in 1978, and that to generally like cost-aware stopping rule with a guarantee. And like in 2026, we're talking about 48 years here with a full surrogate model handled to them on day one. So for your agent loop, it had only like maybe 3 years so far, since it became a little bit popular, and they don't have any model of the task at all. What I mean here is like nobody's being lazy here. It's just like this is a new field, and they're just like trying to attempt the general case, and the thing is like the general case is the one that nobody solved before, and that's why the third columns is actually empty, as we saw earlier. And that's what I mean when I said it wasn't gotcha. It was not like, whoa, they were so wrong, these teams were smart, just like how the system should be designed in the first place. And this is like your answer here. So to one question, which is like, should we just wait for the frameworks to fix this or not? Because the answer and the harsh reality is they're not gonna fix this. And the reason is not because they're bad at their jobs or they're lazy. The reason is like you're asking them for a stopping rule on a task that you haven't defined yet. That's like up to you. And also like nobody can do that besides you. because this is like not like roadmap item. This is actually category error in the first place. So if you're waiting for a specific like framework fix, I advise you to stop waiting that, because the only fix possible here is on your side, and that's the only way forward. So now here's the actual like shape of the answer, and like everything like everything else in this block is actually special case of this one picture. So we're gonna have like task state on the left, real state like not vibes. We're gonna have like 41 test failing. Residual is 0.071, as you can see here. So for this one, like these like three sub goals are still open, and those are numbers that exist whether or not like anybody would ask the model about them. So these always would exist in this case. For second thing is mu, which is like in the model in the middle. For this one, it's gonna read the task state, and it's gonna return a number. This number is gonna be deterministic, so there will not gonna be any model call for this one. It's actually function. And in the math sense, it's gonna call it twice, and then you're gonna get the same answer twice. So that what does deterministic means here. For the policy one, which is on the right, as you can see here, so basically let's say when mu hits 0, that means like you're done. So but if mu stalls, then you can also like give up, which is also another case. So basically it's either like hit the cap or timeout trips. Both cases you just like the task was gonna get killed. So for this one, like we're gonna have like three different endings, and the policy knows which one it's actually in. And here like the model on top, as you can see, so it's just like up top, it's like the proposal, it suggests the possible next move. It's gonna get like a vote, but does not get the vote. It's not basically like does not get the vote. And now I want you to look at the dashed line in the middle. As you can see, let me zoom in a little bit, because the model cannot reach mu. So the measure here is not the thing that being measured, because basically like that's it in the whole sentence. That's the whole design here. Everything else is actually detail. And this is actually the same move as the fuel gauge, by the way, as we talked earlier. So for fuel gauge, basically it's not wired to the engine's opinion of how much fuel is got. Basically it's like a float in the tank. So the thing being measured doesn't get to say about what actually produces. Okay. Now. And like before, like anybody tells me like all this is just like a bunch of theory. So for residual based conversions test, let's say it's been sitting in the continue condition. So for this one, it's actually a task aligned measure, and that's mu. For the model that never certifies conversions, that's actually failure mode 2. Which is actually designed out on purpose. For the depth cap, it's actually backstop, so the cap's still there. The thing is like basically like the thing that it's not like the thing that's gonna make the decision in the first place. Just like a seat belt, it's not like the steering wheel in the first place. And we're gonna have like the oscillation guard. And for this one, it's actually the composition failure, and they're gonna detect it. So basically, like that's like coupler design agent. It's on XZIV, and here's my actual favorite part here, because like they hadn't read any of this yet. Like there's no Floyd, no Cook Podolsky, none of that. They just like had real engineering problem, and what they did is they built the most obvious thing around it, and the obvious thing is correct here. So This is not a research, it's actually design review. Now let's talk about this thing. So as you can see here on the left side of the screen, that's what you actually got. Basically you got it running, and then it's either gonna runs or it's gonna race. So these are two actual terminal states, and capped like run is neither of these states. So I want you to look at the dashed box here. As you can see, that's actually like state your actual framework got no name for it yet. So what ends up happening is it will just like gets filled at as like the first state instead of because it does not have any other way to understand this. And that red arrow, as you can see, is the bug that is gonna be shipped in your production if you're not already like in production mode yet. Now let's talk about the right side. So for this one is like what you actually need, like what actually need to be done in the first place. So it should be like it should like give up, killed, or done. These are like the three different terminal states of the system, and each of these are actually distinguishable. And like specifically at the return type here, we're talking is distinguishable. And you're not talking about log line here because this will not be determined in any string because that was just like gotta grab for, which is not practical. So like every basically like so basically like every mature field has the third one, which for agent case is missing. Basically like let's say for example chess has draw and draw isn't loss, it's its own outcome with its own rules. And this is like an example from chess as well. Set solvers would gonna return unknown, that's first class answer. What that means is I ran out of budget, and that does not mean like basically that also does not basically that means also like there were no downstream tool, which is gonna confuse it with unset. For database, gonna pick deadlock victim, and it's actually had like a named rule for it. So the transaction knows it actually got killed, and it's gonna know that to retry or not. For small agents, basically credit where it's actually due here. So they already have something called max steps error. It's and based on what I've checked so far, it's the only framework in the whole audit of the whole different AI agent systems where actually there was capped trans, which is distinguishable at the type. So to summarize, 99% of the time, like if you had that system design, then your system is capped at 2 cases instead of 3, which is the whole gap and the whole issue behind what happened or what's going to happen to you once you're in prod. Okay, so now let's talk about like best win in the whole video here. Like let's go one layer down, and for this one it's actually already running on the machine that you're already watching this on, and this is what you can see here on the screen. It's actually a TCP. So the one that you can see right here is actually TCP congestion window, and basically it's gonna like slow start, which is like the exponential bit at the front, then the congestion avoidance, which is like the linear sawtooth. So what's gonna happen is like loss event, which is gonna halve it, then it's gonna like climb back up, which is like additive increase, and then like multi proactive decrease, etc. And as you can see, like this this like red dashed line across the top is the rwnd, and it's actually like the receive window. So like here's like the thing that everybody was gonna miss about this whole story here. So rwnd already exists. It was already existed like even before Jacobson, before 1988. It was there. It was actual wheel bound. It was correctly enforced. but and also like nobody had bug in it. And the for the congestion collapse case just like happened anyway, although all of that together was the case. So the reason of that is like rwnd protects the receiver, and it's gonna stops you like basically it's gonna stops you overwhelming the other end, but it does not protect the network in the middle, which is the gap here, and the network in the middle is what fell over in that incident. So the bound was real. It actually was, the only thing is like it was bound in the wrong thing. That's the actual problem here. And what Jacobson like did here is actually he added in 88 was second window. So the second window was like cwnd, and it was driven by observed laws, and like it was actual measurement of the thing that was actually going wrong. And here like the whole fix is 4 characters of C, which is like min of cwnd and rwnd. That's like the cap and measure, and basically what you should do here is you should always take the minimum. And I gotta be really precise here, cause like people get this wrong many times. So what he did is he did not remove the cap. rwnd is still on the expression, still doing its job. It was like never enough on its own. So now let's go back to your agent case. So max iter is rwnd in your case. It's actually real. It's correctly enforced, and actually it's bounded the wrong thing. That's the whole issue. So you won't delete it. You're just gonna add the other one and take the minimum. So same failure, just like gonna go one layer down, and this like been sitting in your kernel since 88. Okay, now let's talk about the 5 questions for your next design review. So let's say on next Monday you're in a design review, and for that you're not gonna read the trace because that's not your job, and you shouldn't even like want to be in that job in the first place. So basically we're gonna have like 5 questions here. So the first question is like what number would get smaller as this task get closer to done, and also like where it's actually computed. And here I want you to actually listen for the word roughly, because roughly is the answer here. There's no actual measure in most of the cases. You need to manufacture it, as I told you. Second question is like if the model says it's done and it's actually wrong, what's gonna catch that? Third thing is like you need to ask them to show you the return value of run that actually hit the cap. So how the color we're gonna know in the first place that happened. Fourth thing is like your planner and your executor. Each of these is gonna have like limit. So the question would be like what's gonna bound the pair of these, because as we explained earlier, both of them can be right, but when they put together they're gonna produce something that is not right. That's the simplest way to put it. Fifth thing is like if a tool calls hangs forever, in that case like which our limits was gonna fire to prevent us from getting billed thousands of dollars, just to prevent that type of issue. And for all of these, like you don't need to read the trace. All you need to do is like you need to watch your team answers the question. And because like 1 and 5 have answers, so any good team would have thought about these ones. And if your team didn't thought about this one, it does not mean they're bad. It's just like this is the thing that they should think about. So your production system, your internal tool, whatever you're gonna use AI agents for, it's not gonna backstab you and gonna bill you like thousands of dollars for, and will never stop working in the first place. Will not even like produce the desired output. So that's the main thing that we need to get from this video. And just like two limits, like two honest limits here before I wrap this whole thing. I mean, I've been talking for too long now. Because for this one, I'm not gonna sell you something that super clean and like that's the only thing like the solution is that simple. There are no drawbacks because that's not how real world actually work. So first one is like this is a systematic random walk. So basically like expected change per step is exactly zero here. So there's gonna be like no drift, no progress in expectations. Like, and if you're gonna terminate with probability 1, that's a theorem, not a maybe, and it's gonna hit 0. Second thing, and the expected time to get there is infinite. Third thing is like at the dollar step, the expected cost was gonna be infinite as well. So in other words, like almost be sure that termination is actually a theorem about eternity. So positive is almost sure about termination, which is like theorem about your invoice. This is theory, it's not a practical thing. And if anybody like shows you proof that your agent would terminate almost surely 100%, then you need to ask them which one they actually proved here, because it definitely is gonna stop eventually. And the expected bill is actually unbalanced here, unbounded, like it can be at the case we showed you earlier, like over 40 grand. So it's not like something that you can just like take with like believe without a grain of salt on it. And now let's talk about the other direction here, which actually matters too. So I want to be straight with you here. So we're gonna have like zero drift, still gonna terminate, which means like no expected progress, gonna do or like prove termination. So the criterion is sufficient, which is not also necessary. So I'm not gonna pretend it's tidier than it is. The second limit is actually one of the biggest one. So let's say for example if mu is gonna hit 0, so in other words measure is gonna be exhausted and the task is 60% undone. And this one is actually the specification gap, and your measure was actually proxy here. I don't know if you watched the different like older videos when I talked about proxy when it comes to agent, etc. Maybe you need to refer to that to understand better what I mean by proxy here. But just let me wrap it out and try to simplify it. So basically the proxy here is like messenger does not tell the deterministic like the actual reality, just like approximate of what's actually going on. And for this case, like the proxy bottomed out before the work actually finished, so all your tests passed and the feature is still wrong. So in other words, nothing in this video closed that gap. I'm not gonna tell you like this is like gonna solve your problem 100%, because that's not how the real world actually works. And I cannot sell you fix for it either, because nobody else even can. So here's now the honest version of like this whole 1 hour and a half so far. Like what the honest version is like every system I showed you that gets this right has computable residual sitting there. We're talking about test, numeric error bound, proof obligation, and all these were not actually locked, and it's not those teams were smarter than you. So the real problem was never make agents stop in the first place. That was the wrong way to talk about the problem in the first place. The real problem here is how we're gonna manufacture residuals, and this is actually like a research problem, and this is like the thing that in your place I'm gonna fund here, because like everything else in this hour is engineering. And now let's like the part that I generally have a hard time being calm about it. So for 1990, like Cohen and Lovitsky, they define a persistent goal. One, it believes P is currently false. Two, it wants P to be truly eventuality. Three is it maintains two until like condition this happen, which is like should believe that either P is true or not. or the other one is like P will never be true in the first place. So that's like actually terminal failure state, and this one is actually formally specified before. And the agents like fields on flagship journal as well. So that's been happening like for the last 36 years so far. So for the gave up, what that actually means is like this one is what they've been talking about is the third state that we discussed earlier, the one that all the frameworks doesn't have. So you need to engineer it by yourself. And this was like the definition of what an agent is before even like most engineers were even born, that they start working on AI agents or machine learning in general. And actually it's get even worse here, cause like Kinney and Gargov like 91. So basically they didn't just like theorize about this, they run the experiment. We're gonna have like, they had like two axes, how fast the world changes and what deliberation costs you. And what they've actually found here is like bolt agents, let's say about ones that rarely stop and reconsider. What's going to happen here is like they're going to win when the world changes slowly. For cautious agents, they're going to be like constantly reconsidering, and they're going to win when the changes happening fast. And for your LLM agent, it's actually here. So basically like it's gonna consider the entire plan every single tick, and at maximum deliberation cost, because like every reconsideration is a forward pass that you're actually paying for, and an environment that's gonna change slowly because like your code base isn't moving while the agent thinks. So that's the solution here. But the worst corner of that chart here, which we need to discuss as well, is like as it was predicted before in 1991, and also like in for Brightman like in 87, they also gives you the why behind that. So the plans exist to foreclose deliberation. So that's what the plan is for, and it's a commitment that stops you to redecide in every 5 seconds. So in other words, like an agent that rederives its intentions every turn doesn't have any intentions in the first place. It has like only opinions. It's not deterministic. So that's gonna be run forever, and you're just gonna pay for it because it's not decisive in the first place. So now to wrap up the whole video here. So the word agent was actually been used, but the actual field was not. It's existed like now for over like since like the 80s and 70s. It's not something new. And if you're gonna take one thing out of this 1 hour and a half so far, the thing is like your agent has a fuel gauge where its progress bar should be. And now you know why that's not a metaphor here. It's actually fuel gauge because it measures a resource that you're actually burning, which is credits. And it's not progress bar because progress bar gotta be a function of the work in the first place, and nothing in that guard has never seen your work before. So now let's talk about the next thing that you need to do now. These are like the practical things of this video. So let's say on Monday you're gonna have like design reviews call. So the 5 things that you need to do: you need to like to name the number that goes down, and you need to put it in the guard, like inside the code base, and not like inside some prompt. So because like the prompt does not have any control over the actual system. Second thing is like you need to demote the model to proposer. So it does not get to certify its own completion. Basically like the same as the fuel gauge, because like the thing being measured doesn't get a say of its own. Third thing is you need to have like 3 terminal states with like distinguishable at the return type. So basically done, gave up, or killed. You need to have these different 3 states. Fourth thing, you need to have like time fuse for hangs. For example, like an iteration fuse for iteration fuse for spins, and both of these are actually different instruments as we've seen before. And right now you probably got two of the same one, and you probably think you're already covered, but you're not. And the final one is like bound the system, not the loop, because you're gonna find every place where two cat things are gonna call each other, and that's where your or another clients like 47 grand happened because of that. That's the reason behind it. And none of that's actual research here. It's actual this is like actual practical advices or tips on what you should do next, and all of it you can do it by this week. So if you're deciding whether to ship one of these features or this tool or production system you already have or something, and you just like need a little bit of help, you can email me directly. You can just like send me the architecture, the overall architecture, and I'm gonna send you more detailed information on how you can approach that. So that's all. If you like the video, just like put like and put like comment on what you think about anything in this video, and that's it. Take care, bye.